Matt Hegarty here, Harvard College class of 1982 and president of the Harvard Club of Boston. First, our club land acknowledgement. The Harvard Club of Boston is located on the traditional and ancestral land of the Massachusetts, the original inhabitants of what is now known as Boston. We pay respect to the people of the Massachusetts tribe, past and present, and honor the land itself, which remains sacred to the Massachusetts people. And we're absolutely delighted to welcome everyone to our Saturday of Symposia, which is a joint program between the Harvard Club of Boston and our great ally, the Harvard Alumni Association. I want to thank you in particular for joining for what is the 41st Saturday of Symposia. The last two, of course, have taken place virtually, but it's my sincere hope that next year in 2022, that those near can participate here at the clubhouse and those far can participate via remote means. So stay tuned for that. While we may not all be physically together participating in these lectures this morning, I'm happy to see that we're all coming together nonetheless for this day of learning and engagement, which has occurred over the past 5 decades on the first Saturday of December. A little bit about our club, and I encourage people, if they're in the neighborhood, to stop by the clubhouse, or at least if you're far away, hop on the website. It's a real festive time of year here at the Harvard Club, and we'll hope you'll visit us. Our in-person gatherings and events continue to be quite successful. I had classmates of the class of '82 here for a Harvard Yale watch party a couple of weeks back. And there were many other classes represented there. So it's a terrific place to meet old friends and new. And there's a lot of energy here at the world's finest city and alumni clubs. So hit me with an email at president@harvardclub.com if you're in the neighborhood. This morning, you will be participating in one of 2 lectures by our esteemed Harvard faculty. One with Professors Ann Blair and Leah Whittington, and the other with Professor Finale Doshi-Velez. Now, immediately following these lectures, we're going to invite you to join each other in virtual breakout rooms where you can discuss the lecture with fellow attendees. It's almost like you would discuss the lectures over coffee here at the club, or, you know, if you harken back to your undergraduate days, how you would discuss the main lecture during a section. Only we won't have the section leader giving you a hard time this time around. Then we're going to reconvene at 1 o'clock on Zoom again for today's keynote lecture with Professor Bridget Terry Long, who's also the Dean of the Harvard Graduate School of Education. So I look forward to seeing you all at some point today. And many thanks to those who made today possible. Christy Burns, our Director of Member Events here at the club, Jan Saragoni, who's head of our Membership Engagement Committee, the great Marlene O'Brien, who actually is the chief architect of this great event. And with the HAA, Chris Owaki, Angela Wright, Heather Gaines, and the estimable Philip Lovejoy, all of whom made today's symposia possible. Thanks again for joining us. With immense gratitude, Veritas.
Good morning. My name is Carlos VTC, and I'm on leave for the World Bank at Harvard Paulson School for Engineering and Applied Sciences. It is my great honor to introduce Professor Finale Doshi-Velez, a thought leader in artificial intelligence at SEAS. Before we begin, a few housekeeping items as well. We have closed captions. If you want, you'll be able to press the CC button on the bottom right of your screen. We'll have a 45-minute presentation followed by Q&A. If you have any questions, send them to the chat room to HAA Q&A. Let's begin. Before joining SEAS, Professor Doshi-Velez started her journey on the other side of Mass Ave at MIT. After a double major in physics and aerospace engineering, she continued in the Institute for her master's in computer science. The Marshall Scholarship took her across the Atlantic to study engineering at Trinity College. In 2009, she returned to MIT for a PhD in computer science. and became a postdoctoral researcher at the med school. Joining season 2014, Professor Doshi-Velez earned various awards, culminating in the NSF Career Award and the Sloan Fellowship in 2018. Just this month, her contributions to the field were again recognized with the Anita Borg Early Career Award, recognizing substantive contributions to the field while increasing the participation of women in computing research. This recognition comes while SEAS is undergoing a lot of change. Dean Doyle inaugurated the new 500,000 square foot science and engineering complex across the business school between the iLab, the Life Lab, and the Launch Lab. As if to preempt these increasing confluences of interdependent networks of researchers, Professor Doshi-Velez exemplifies interdisciplinarity. She has worked closely with the medical school, the law school, the engineering school, as well as various hospitals and even the VA. This multifaceted collection of diverse institutions comes together into a single nexus under her leadership at the Data to Actionable Knowledge Lab. DTAC uses probabilistic methods to address many decision-making scenarios involving human and AI. Their work spans application domains such as health and wellness to broader socio-technical questions with human-AI interactions, AI accountability, and responsible and effective AI regulation, such as responsible use of AI by banks. In fact, globally, DTAC will join efforts to engineer a new Bill of Rights for an automated society so that it does not become a parchment guarantee. Professor Doshi-Velez recently received tenure from Harvard, recognizing not only her cutting-edge AI research, but also her work in diversity, accessibility, and inclusive openness in all aspects of her teaching and research. In fact, I count myself among the pilgrims to her weekly, year-round online office hours, whether in Brazil, Washington, D.C., or Cambridge. After bringing DTAC insights to global regulators, it seems I will again have the privilege to bring her research to high-level decision makers. Here to open our Saturday Symposia's 41st program, 43rd version, with the Harvard Club of Boston and the HAA, the Gordon McKay Professor of Computer Science, Finale Doshi-Velez, will speak on artificial intelligence that works for people. Professor Finale.
Thanks so much for that introduction. All right, let's get started. So as Carlos mentioned, I work in the AI space, and I'm particularly interested in trying to figure out how we can get AIs that will work for people, with people, in settings where there are human decision makers that are relying on AI systems to make better decisions. So let's dive in. So, and one thing that I was part of recently was the AI 100 report, the most recent version of this. And so the idea with this report is like every 5 years, a team of people looks at the most, the advancements that have happened in AI over the last 5 years and documents them. And the idea is that this documentation will go on for 100 years. And as we were looking at the last 5 years of AI, I think the thing that's just truly incredible is not only things like AlphaGo, besting the best human Go players in the world, but how AI tools have become just so commonplace. Many folks have probably used voice recognition systems of various kinds. Back when I was in grad school, I had to really modulate my voice low, and even then it was hard to get a voice recognition system to understand me. And it was trained for a particular, deep Midwestern male accent, and that's all it would understand. And these days, my kids can ask Alexa to fart. They don't even have their R's, and it makes fart noises, right? It's just we can get our menus translated by just putting our camera on top, and so just the commonplaceness of these AI tools is just really incredible. How they touch us in so many different aspects of our lives. And I was talking to a couple of colleagues who mentioned how the autocompletes or the recommendations for your filling in your email responses have gotten like scarily good, right? Like we seem, it seems to know, like, should you respond with a sounds good, or let's chat about this later, or whatever it is. So they seem really smart. But on the other hand, we see AI tools making what seem like incredibly stupid mistakes. Take an example of the stop sign in the picture. By putting just a couple of pieces of tape, so we're not even tampering with the camera or the phone or anything, we're just tampering with the stop sign itself, the physical sign itself, we can get an AI, which is trying to recognize traffic signals and traffic signs, to go from classifying this as a stop sign to a speed limit 45. Very different interpretation, right? And there another somewhat recent example when it comes to translate, I was just saying it's amazing you get your restaurant menus translated, is that you take a language that doesn't have gendered pronouns, and then you convert that into English, and the pronouns it chooses are very gendered in terms of stereotypes. And it's like, why does it do this? Why does it make these kind of mistakes? And so what we're going to be doing in the next 45 minutes is talking about, why do these mistakes happen? Why do AIs make the kinds of mistakes that they do? And how can we mitigate these drawbacks so we can get all of the benefits? Because it's so clear, again, that AIs have just integrated themselves in so many common settings throughout our lives, as well as major stakes types of settings. All right. So to understand why AIs make mistakes, one thing we need to think about is, how do they work? And in terms of the very, very basic high-level overview of how AIs work, there's three major components. There's the stuff that goes into the system, the inputs. There's the model, that's the system itself. And then there's the training criteria, sometimes called the loss. What is the system trying to do, right? You give it a goal. And one big difference between AIs and other more rule-based type systems is that the way people design AIs is not to necessarily design the model, but they choose a criteria. They say the model will be good if it does a certain thing. Now, model, go figure out how to do that particular thing. So just to make this whole idea concrete, we could have a scenario where the inputs are pictures. So for example, pictures of cats or dogs. It goes into the model. The model is very complicated, might have hundreds of thousands of nodes, millions of parameters, and even more. So it goes into the model, and the model maps this picture into some space, which is, in technical terms, often called a representation. And in that space, whatever this space is, this abstract space, it draws a little line and says everything on one side is a cat and everything on the other side is going to be considered a dog. And then it figures out, checks how good is this line that I've drawn. And the line is good if the guess that comes out, cat, is equal to the true label, cat. Right? And so it tries to figure out where to put this gray line so that you match, the picture matches the label that comes out. Right? So this is, again, a very high level how these systems work. And one thing to note that we can tell, even from this very high level view, is that in general, modern AIs work best when there's a lot of data that effectively covers the task. And what I mean by that is that if you have lots and lots of pictures of cats, you fill up the space with cats, you fill up the space with dogs, it starts becoming very obvious where that gray line should be, because you've kind of covered that whole space in terms of options. And a version of this kind of relates back to the example that I gave at the beginning, where if you've only trained on a certain accent, then that's the part of the space you've covered. And then you encounter a new accent, and you may just have no idea what to do. It doesn't know how to map that new accent into this abstract space anymore in any sort of sensible way. So what could go wrong, right? And that accent was one example. Well, you might have some trouble with the inputs. So let's take these two examples over here. We have pictures of cats. We have pictures of dogs. We asked the model to do that task. Remember, we were trying to classify dogs and cats to try to figure out, is it a picture of cats or is it a dog? And it does its thing. It learns its loss. And once it's done this entire process, you feed it this picture. And it comes back with dog. Well, what might have happened? We go back to the original data, and we notice that all the cat pictures are indoors. And we notice that all the dog pictures are outdoors. And because the dog pictures are all outdoors, the easiest way to tell with these nine examples from each case, whether something's a dog or a cat, is to simply look at the background and see if you see green in the background, you classify it as a dog. And you might be looking at this and be thinking, oh, this is massively contrived, right? Like, how would this happen, right? You have lots of data coming in. And you picked these outdoor dogs, they're indoor dogs, and you pick these indoor cats and blah, 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 right? But this does happen. And this, in fact, is one of the biggest reasons why AI tools fail. In terms of things that have happened kind of in recent history, there was a case where Apple Card didn't see gender, or was discriminating based off of gender when it was determining who's at more risk for credit. Also recently, there were situations where there was racial bias in medical algorithms that favored white patients over sicker Black patients. And in both of these cases, what was going on is that there was already something embedded in the data, and the model was just replicating that. For example, in the case of patients, what was going on is that the Black patients were not utilizing the healthcare system at the same rate as the white patients because of issues around access, et cetera. And so it looked like they were less sick just because the model, when trained, was looking at the number of times, I'm simplifying, but the number, imagine the model could easily learn, hey, the number of times you visit a healthcare system is how sick you are. This is kind of like saying, well, if the background has grass, then it's a dog, right? Because it's not actually measuring your illness, it's measuring the number of times that you visited the healthcare system. So these sorts of issues that seem kind of like, oh, I would never do that, actually come up a lot in real life. And I would say that in terms of reasons why AIs don't do the things that we want or the things that we expect, almost, or a majority of the time, comes from the fact that the inputs already had some bias in there. If you look at sentences on the internet, you may find heavy gender biases when they talk about different professions. So of course, a translator trained on that sort of data is going to replicate those biases. That was inputs. Other places where models can go wrong include the model itself, or the AI can go wrong. And here I point to an example of the mortgage crisis 2008, where there was a mistake in how likely various losses were expected to be. The idea was that if one person doesn't pay back, then another person, that probability is independent of another person not paying back their mortgage. But as it turns out, these things are correlated, right? If something rough is going on in a particular area for a group of people, they might all default at the same time. So sometimes it is the case that models are the issue, but I would say that more often it's the inputs that are the problem or the loss. And let me give an example of that final case. So this is a bit of a toy example, but I'll connect it to real life in just a moment. So imagine you have a robot and you've told the robot to clean up all the dirt in your house. And the way you would choose to encode that is say that you get +1 for every bit of dirt that you pick up. It seems like a very reasonable way, right? Remember, when we train an AI, we don't tell it exactly what to do. We tell it how does it win? And then we try to get it to figure out how to do that particular task. So in this case, the most direct way to pick up the dirt involves pissing off the cat. You have to go back and you have to think to yourself, okay, +1 for each bit of dirt that you pick up, and don't bump the cat. Okay, so now cat is happy. Robot goes around, picks up all the dirt. And what happens next? And if any of you have children who get rewards for doing cleanup, like we experimented with for a certain bit of time, you know exactly what happens next. The robot chucks all the trash onto the floor so it can get more +1s for picking up the trash. And this actually happened in my house. We have candy after cleanup, and one day the kids decided that they wanted 2 candies. So off the crayons went onto the floor to be cleaned up again. And they were like, but now we did a second cleanup. Do we get a second candy? So what I want to point out here is that it's really hard sometimes to design this loss function, because you might overlook, things like the cats, but you might also overlook these kind of failure modes where once the robot picks everything up, it wants to toss everything back on the ground again so it can pick it up again because it gets rewards for picking things up. All right, so that was a really high level overview of how AIs work and the 3 major categories of places in which they can go wrong. There's the inputs, the models, and the choice of the loss, the way you tell it how winning happens. So now what I'd like to do is dive into a bit of examples from my own research, talking about what can we do about it, right? These examples, these issues exist, and what are ways to handle this so we can, again, we want to get the benefits that AIs have to offer without them making these types of stupid mistakes. So the two things that I'm going to talk about are first, the importance of validating in many ways. So in terms of things that you might take away from this presentation, is that there is no one way to validate an AI system and then just know that it's going to work. You need a couple of different ways looking at the AI system together. And then as a whole, they represent your confidence that it's, again, not going to make stupid mistakes. So the example that I'm going to give for this particular case is an example of managing patients with hypotension in the ICU. Here, our goal is to reduce the mortality of patients with sepsis. And the how is that we want to make better fluid and vasopressor choices. So both fluids and vasopressors are ways of managing hypotension. And we're specifically interested in managing hypotension for patients who are very, very sick. They're in the ICU and have sepsis. So as we looked at this problem, we were given a data dump from the hospital that we were analyzing. We considered that there's two major categories of approaches that are out there. One is the model-based approach, right? So now we're getting into some of the technical elements, where we explicitly think about the future. So we think that the patient is in some condition or some state. You're giving them drugs, you're giving them the fluids, you're giving them the vasopressors, and that changes their state over time. We don't get to see what's going on inside the patient, right? It's all squishy and complicated. But what we do see are measurements. So we might see their oxygen, we might see their blood pressure, we might see their lactate. And based off of the measurements that we're getting from the patient, we might not have all these measurements at every time point. We want to try to predict what state they'll go into the future and how their disease might progress based off of the choices we make. So that's explicitly thinking about the future, right? Like I give this drug, it's going to move this patient into, for example, a better blood pressure, and that's what I want to do. The alternative is a more neighbor-based approach, where you don't explicitly think about the future, but you just think to yourself, hey, I've seen a patient in that condition before. And last time, or the last couple of times, when I saw a patient in that condition and I tried the fluids, they had good outcomes. Whereas when I tried the vasopressors, the outcomes were not so great, right? So you have your patient, you look for nearby patients. And the advantage of this is that kind of implicitly you're synthesizing like everything about the patient's history. And you have some intuitive notion perhaps of like how patients are similar to each other. And you're using this to make forward predictions in a very complicated disease setting, right? To write down this sort of disease model here is quite tricky. So this might actually be a better bet. So in our research, what we did is we had the following insight, is that sometimes, hopefully, you're lucky enough to have similar patients, right? Your condition is not unique. There have been patients before you who are in the exact same condition. And because there were patients before you in the exact same condition or very similar condition, you can look at what worked for them. However, if you are unlucky and your version of like how you're sick is just really distinct from everyone else, then maybe it is better to work on a simplified model of how disease will progress. Oh, right, fluids might be a bad decision because we've already given some fluids in the past. We don't want fluids being retained in the lung, et cetera, et cetera. So you think through it much more analytically about the consequences. Your thinking is approximate, but hey, that's better than mapping yourself to a patient who is not actually very similar to you at all, right? So our insight was that maybe you don't have to choose between these two approaches, but actually the appropriate thing to do is to choose the approach based off of whether you have similar patients to you or whether you don't. So this is a cool idea, and we've used it many times in our healthcare applications. And in this particular case, we applied this idea to about 15,000 patients from the MIMIC data set. This is from Beth Israel here in Boston. And the thing that I want to point out for the purposes of this presentation, this talk, is that we use a recurrent neural network, that's what an RNN is, with 128 hidden variables to compress the history. So we took the patient's history and we compressed it into 128 numbers, right? Remember in that very early slide, this idea of like you take the picture of the cat and you map it into some abstract space. Here, our version of this, our instantiation of that was to take the entire patient history and map it into 128 dimensional space, which by modern standards is not particularly large, but it's kind of a big number, right? You can't look at 100, like a human being cannot inspect 128 numbers. We're going to get to that in just a few moments. The choices were different dosages of vasopressors and fluids. So when we did this experiment, we did this, so recurrent encoded means including the history, non-recurrent encoded means not including the history. Physician is how well the clinicians were doing as a baseline. And then these are different models. Kernel is looking at neighbors, DQN is creating a model, and these were our mixture of experts done in a couple of different ways. The details are not important, but the part that I want to point out for the moment is that in our estimation, and remember, it's a little tricky, right? We're not going out and we're not just applying this on patients because of all those issues, right, that we talked about where AIs can go wrong. When we analyze something, when we take a batch of data and we come up with recommendations, the first step is not to go try it out on a patient who is seriously ill with hypotension in the ICU. The first step is just to see, can we use statistics to tell us how well it might have done, right? Because if the statistics say it's bad, then there's no point in continuing onward. We have to go back and do some adjustments. So that's what we did. We ran some statistics. Again, the details of the statistics are not important. They look like the numbers are higher, right? That's all I want you to take away from this part right here. And then we tried to make it a bit more intuitive. So we said, okay, at the bottom axis is how much does the clinician differ from our recommendation. So 0 means that in the batch data, in the retrospective data that we collected out of the data set, the clinician usually did what we told them to do, or we would have told them to do, like our AI would have told them to do. And then higher numbers and smaller numbers are saying that, hey, the thing that the clinician did was actually quite different from what the recommendation, our recommendation would have been. And we see these kind of U-shaped patterns when it comes to mortality, which is on the y-axis, which suggests that, hey, whenever the clinician did what we would have recommended, recall we trained that after the fact on the batch of data, mortality seems lower. And when there was a big difference, mortality seems higher, except for this kind of, we're not sure quite what's going on over here, but it kind of looked like, okay, maybe this is somewhat promising. Then I had a couple of students, this was part of a course project, kind of connecting, all the research and the pedagogy together. So there were some students who were just trying to test this, their code for creating these sort of plots. And so they tried it out with a random policy and also a policy that never gives treatments. And we know that sometimes you got to give treatments, right? We know that it's a bad idea to never give treatments. And what we discovered is that these curves looked awfully similar to the policy that that we recommended. So optimal policy is our recommendation. And then in green and black over here is how we believe doing no action would have performed. And this is really funky, right? Like, again, this should not look like this. And as we dug into this, we realized it's not the numbers are wrong or something like that. It's just that this way of checking for is this reasonable has some major issues with it. And in particular, most of the time, nothing is the right action to do. So you recommend doing nothing and the clinician did nothing. If you look at a time series of all the times patients are intervened on in the ICU. So you end up with 0 and 0, 0 minus 0 is 0. So the patients who are doing the best often end up right here. And then where are opinions likely to differ? Well, opinions are likely to differ when the patient is sick, right? Or particularly even more sick, right? They're all sick, they're in the ICU, but doing particularly worse. So when the situation is dicey, that's when the clinician is taking actions. That's when the AI is recommending actions. And that's the time where you're going to see more difference. Just in general, they're not going to necessarily quite align. And you end up with this shape over here. So this is disturbing, right? And the key point here is that we need more than statistics for validation. Again, if these plots look bad, that would have been a smoking gun. And we would have known that we need to do something more before, passing this forward. But the fact that these looked good is not sufficient to say that this system is not going to make stupid mistakes, that it's a reasonable system. And it is this sort of thing that has started our quest, or it involves our quest for both models that can be statistically validated, but also are human inspectable. So let's go back to that question of do we really need 128 hidden variables in that representation? We're pretty sure that people don't have things that are that complicated, and they're making reasonable decisions in the ICU, right? So we had two key ideas to try to make this a smaller, to try to do as well on the task, but make the problem smaller. And the first one was to start with a model of disease that's just focused on the hypotension decision, right? Because if you try to squeeze the entire history of the patient, you're squeezing everything about their renal function, their respiration, all of these different things, in addition to things related to their circulation or their blood pressure, their hypotension. And maybe we don't need to know all of that, right? What if some of these 128 hiddens are encoding details, again, about that patient's renal function? We don't need that. And so that was one thing that we observed. It's maybe we can make this smaller by creating notions of, what's your patient state or patient condition is what is your hypotension type condition, right? Versus your overall condition. The other key idea that we used was that we were only going to focus on situations where doctors disagree, which, if you think about it, is a really sensible way of trying to use data that's already been collected. Because suppose that the doctors always do a particular thing when the patient's blood pressure is at a certain value. Then from a statistical perspective, from an AI perspective, we don't have coverage, right? We mentioned at the very beginning that AI systems work best when they have coverage of different examples. And there's no way to extrapolate how would doing another treatment have worked if the doctors are always doing treatment A. Whereas if you're in a situation where sometimes doctors do A and sometimes doctors do B, then maybe that's the place where statistics and AI can help, because then ideally we've seen the different outcomes that come out when A happens and B happens, and we can try to recommend which of those two branches are the best. So in terms of this, just trying to make it a little bit more intuitive in pictures, imagine that you have a couple of patients, and these are the patients evolving over time. The color represents their state or their condition. And the thing inside the circle represents whether, what action is taken. There's two actions, action 1 and action 2. So we notice that whenever the patients are in these blue states, we're taking action 2. And whenever the patients are in these lighter blue states, oh, there's a little mistake here, they're taking action 1. And then there's most disagreement in these yellow and red conditions. So what we do is we compress things down and say, here are the places where the differences are really important. So let me turn this cartoon into real life in terms of what we did. And this looks big and complicated, but what I want you to take away from this picture is that it fits on a slide. So what we did is we looked for those places where doctors disagree in cases that are relevant to hypotension, right? So relevant and disagree. And we found 14 situations where they disagreed. And for each of those 14 situations, we could plot various values, right? And again, looking at what they are is not important. What I want to emphasize is now, instead of 128 dimensions varying all over the place, this is a picture we gave to our doctors and said, okay, does each column make any sense to you? Are these particular forks in the road when you consider what happens to patients? And they were able to interpret all of them. It was suddenly human inspectable. And then for each of these 14 situations, we were able to check What is the policy if you use different reward functions? So these are 3 different reward functions. And we could say that, your choice of loss, remember that loss about, do you avoid the cat or not? Well, imagine trying to tune a loss for hypotension. I mean, you know that it's bad to have too low blood pressure, but is it quadratically bad? Is it linearly bad? Is it some piecewise function that goes down and then goes back some other way? It's really hard to know exactly how to design this loss function. This problem is now suddenly small enough that we can describe for different choices of loss functions, what would the policy look like? And again, the point is that it fits on a slide, right? I'm not expecting anyone to be able to interpret this. This is for the clinicians to interpret. But these are pictures that they can look at and say, hey, this is weird, right? Probably something in your input data is wrong, right? You're missing a particular variable that have distinguished this type of condition from this type of condition. All right, so that was the first major segment, right? What can we do about it? Validate in multiple ways. And we talked about validating from a statistical perspective and also from a human perspective, and really trying to make these models small enough so that humans can look at them and inspect them, especially in a high stakes scenario like in the ICU. What's the other thing we can do? The other major factor of the 2, right? So validate in many ways, is that human factors matter. And the illustrative story that I want to tell from our lab here is around the question of antidepressant prescribing. So the goal here is to treat patients with major depression, and how we're going to do it is by recommending antidepressants. And what we realized here is that there's many ways to provide that information about what the model is doing. So I'm giving you just 2 really quick examples here of a system. You can imagine a system gives some patient details. It gives a recommendation of what drugs you might want to give a patient. And then it says, why are these recommendations being given? Is it because the patient has diabetes? Is it because the patient has high blood pressure, et cetera, right? And here's another way of providing an explanation. Instead of saying that these are the major features, I could say, well, here are the following rules of thumb that are the most important for this particular patient decision. For example, if concerned for QT prolongation, favor sertraline and avoid citalopram. And what we did is a study where we could control whether the recommendations were good or bad. So it's called a Wizard of Oz study, not a real study. These are not, we made up the cases. And we checked it with 200 psychiatrists. This is in my world, this is a really large sample size. And we had them basically make decisions based off of these sorts of systems with different types of explanations or different levels of inspectability. And what we found, first of all, is that compared to if nothing is given, right, there's no recommendation given. If the recommendation is correct, people do better. If the recommendation is incorrect, they do worse. And that's not ideal, right? We made recommendations incorrect on purpose, and ideally people would be able to ignore an incorrect recommendation and go back to their baseline. But the more interesting thing that I thought was that helpfulness and accuracy were anti-correlated when it came to situations where the recommendation were incorrect. So people really liked this type of recommendation because it was very glanceable, right? You take a quick look, you're like, oh, okay, diabetes, high blood pressure. Those are the key factors. But it doesn't engage your brain in analytic thinking. You just kind of heuristically check it off. And then you might miss the fact that, hey, the system is recommending something completely wonky. Whereas in this case, people did not like it, right? Their subjective rating was low. But what came out of this was that if they were thinking about these rules, they would go like, wait a minute, like if this is the rule, why is this the recommendation? Something makes no sense. And they were able to catch more errors, not fully errors, that's expert over here, but more errors. And these other cases that we also tested a placebo explanation, like because of the data or something like that, just to control for the fact that maybe, or not maybe, it's known that just providing any explanation can change people's trust in the system. So this is really interesting, right? The human factors here were really important, and it's something that we're continuing to work on, where not only do you want to make sure the system is inspectable, right? That's the AI person problem, but you also want to make sure that people are able or will actually do the inspection in the right way at the right time. And that cannot just be assumed, because when people are busy, they're trying to get through their day, they're seeing a bunch of patients. If something can be done quickly, they might do it quickly and end up cutting some corners. All right, so those were two examples from our lab that are really in the weeds. And my lab works a lot in the healthcare domain, as you saw, when it comes to recommendations in the ICU, recommendations in psychiatry, and pointing out the importance of validation in many ways, and also not forgetting about the human factors when it comes to putting an AI system out into the world. Those are really specific examples. And what I'd like to do in the last couple of minutes is to zoom out to the bigger picture. So remember where we started. We said that AI systems have three major components. We have the inputs, we have the model itself, we have the loss. For this purpose, I'm going to change the loss into the outcome, right? Or like kind of what happens when you actually put it out into the world. And the way I like to think about it is that we have inputs, model, and outcome. And we also have some choices about what happens before a system goes live and after a system goes live, ex ante and ex post. For example, the type of work that we were doing in the ICU case was very much an ex ante, right? It was like, before we try this out on patients, we want to check this as much as possible. We want to check it numerically. We want to check it with human inspection. It would be irresponsible to not do all of that checking ex ante before we put it out there. In contrast, the little explanation for that particular patient decision is more like an ex post sort of thing, right? Because then it's out in the world, people are using this explanation. I mean, we did this through a controlled study, but you could imagine that it's out in the world and people are using that explanation. So how do the pieces fit in, right? So I think this is kind of the high level picture now, the summary, if you're thinking about how do we get the good stuff about AIs and not the bad stuff. Each of these categories and each of these settings has specific actionable things that you might want to do, or you should be thinking about doing. When it comes to the inputs, it's so important, as we mentioned earlier, to have transparency about the data collection and make sure that the data is inclusive of the populations that you are going to be using this on in the future, right? And you might have different levels of inclusion that are necessary. Like maybe if you're just building an app to measure step counts or something like that in your basement for your friends to use, it doesn't have a high level of inclusion that's required. But if you put that app out in the world, then maybe it should work with people with different gaits, for example, or who walk on different surfaces, because maybe not everyone walks on a paved surface. So these things are really important. Ex post, you want to track changes in how the inputs are going on. So one big issue that we run into in the hospital setting is some procedure changes. Actually, I think COVID is a great example, where now if you all are in settings where you regularly are taking COVID tests like we are at Harvard, I'm suddenly having to put in information about my symptoms, like, do I have a runny nose, blah, 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 like every week. And this is not data that would have normally been available, right? So the fact that certain data is being collected can completely change the way an AI system behaves. Think back to the case where the Black patients were being classified as being less ill because they had less interactions with the system. There was just less data about them. And if that data collection process had changed, then it would have looked very different, right? So we need to be checking to see, hey, we can't use the same algorithm pre-pandemic as post-pandemic because the data collection process has changed. When it comes to the model, I emphasize being able to do these inspections. And the major takeaway that I will say is that a lot of times people state it as a trade-off. Like either you get a model that has high performance, like high numbers, high statistics, or a model that can be inspected. And it's been my experience and the experience of many others that, especially for high stakes scenarios, these are not orthogonal axes. It is possible and kind of almost like a moral imperative to create models that do both, that get good numbers and check out under human inspection. And then finally, we should be checking those outcomes, right? We should be checking the statistics on how well it works on subgroups and what human factors are important, and tracking changes in performance as well as anomalies. And the last thing I'll just say, these seem like a lot of different buckets, I truly think that managing like AI systems out in the real world is going to be a collective responsibility for two reasons. First of all, the ways in which these systems may go wrong, no one person or no one team is going to be able to think of all of these. So in terms of noticing that, oh, like this, voice recognition system, hey, this is great. It works on kids. It works on, with women. It works across all these settings. But oh wait, it doesn't work on people with MS or other speech dysarthrias. Maybe we should fix that, right? And it's going to be a collective responsibility of surfacing those situations where AIs fall short, because people are not going to, no one team or no one person is going to think of those. The other element that's a collective responsibility here is figuring out what we want the AIs to achieve. And this is a really big change from the past, where we might say, hey, doctors, be reasonable, be responsible. Hey, drivers, be reasonable, be responsible, right? And then if you have a car crash or you have a bad patient outcome, it goes to a court where people are questioned and you kind of determine, was it reasonable? Was it responsible? Was it malpractice? Was it negligence? Here, these things are being coded in from the beginning. And it's so having these AIs is forcing us to think about how we think about ethical principles in a much more ex ante fashion rather than being determined ex post. So I'll finish with that, in terms of, the big responsibilities and the collective responsibilities we have. And I'm really excited to take questions and discussion.
Thank you so much, Professor Doshi-Velez. This is Chris Nowacki from the Harvard Alumni Association. This has been fascinating, and I really appreciate you being able to explain things down, as I'm also a noob to AI, so I really appreciated the introduction and talking about the pluses and minuses. So at this time, we're going to jump into some Q&A, and I'll start with one question that was pre-submitted and then get into some of those other ones that people have asked. And again, if you have any questions, please feel free to submit them to me, H&A Q&A, and I will have you come up. So our first question is, how do you see the application of AI in healthcare, specifically the development of new therapeutics and the identification and understanding of new diseases? And has this changed since COVID has entered our lives?
So I don't know in terms of COVID, I can't say specifically there. I will say that in healthcare, the easiest places, the places where we're seeing the most difference happening are places like imaging, for example, where you have an image and you need to find, is there a tumor, or is the mole concerning, or is it just a normal mole that you don't need to worry about? Those are the cases where we've seen the most benefits, or the kind of, and if you think about it, those are the simplest settings, because all the information about the mole, for example, is in the image. The fact that we now have an Apple Watch and a couple of others, is it Samsung and maybe Fitbit? Don't quote me on this. We have a couple of these wearables that are now FDA approved for AFib detection, which is amazing, right? In terms of what is possible with the, with a wearable that anyone can wear. So I think those are the places where we've seen the biggest advances, or this going from like pie in the sky to like actual commercialization of tools. And again, the AFib detection is something where if you're monitoring someone's heart, then you can detect it out of a waveform. So it's, again, relatively easy task. In terms of new therapeutics, I think that one, or new treatment decisions, I think that one's harder. Like that's kind of the goal. But I think it's and getting to personalized treatments and personalized therapies is definitely the goal, but it's much more tricky because there's many more factors. For example, in psychiatry, where I do a lot of my work, there's a question of, is it helping someone's depression? But also, is it going to be tolerated? And that's a very different question than, is it sorting out someone's depression or not? But again, lots of great work is happening, but I think that that's work that's taking a little bit longer to make it out there into the real world.
Excellent. Our next question comes from Sandro Alessandrini. And so Sandro, if you'd like to unmute yourself and ask the professor your question, I invite you to do so now.
Good morning, Dr. Doshi-Velez. Very, very interesting presentation. I do have a question regarding your modeling with respect to including, especially when doctors disagree. Is there a level of experience means a lot, especially medicines, because some doctors see things more depending on experience. How is that incorporated, that experience incorporated in the modeling? Is weight put in on doctors that have experience versus doctors that don't have as much experience?
So the way we have approached this so far is to almost flip that question around and see whether the doctors who have more experience, their decisions end up being the better ones or the ones that the model also recommends. For example, in the ICU case, this is not something that we've been able to check, but our intensivist colleague is fairly certain. There are situations where the disagreement is whether to do anything or to do nothing. And they are often like, well, the more experienced folks kind of know that if the body is going to heal, it just needs time to heal. A more aggressive treatment might not be particularly useful at a certain point. Whereas the younger folks might be like, I've got to do something. And then we kind of like our algorithms ended up kind of supporting that intuition in the sense that it suggested taking no action more often at those branch points, kind of validating the fact that when the more experienced intensivists in this case maybe say that the right thing to do is just not meddle and see if the body will heal, that might be the right thing to do.
Thank you.
Wonderful. Our next question is coming from Ashish Garg, and Ashish's connection is not the best, so I'm going to ask it for him. How do you explain the persistent failure of IBM Watson to perform medical diagnoses and pass the US MLE exam? How does that impact the value use of AI and medical diagnoses?
Gotcha. Okay, so that's complicated, and I don't know I haven't kept up with all the details in terms of what they've been doing. So let me preface with that. I know that some of these issues came from, like I mentioned, how, as data processes changed, like, COVID, suddenly we're monitoring our systems. There was definitely some data process changes early on when they were implemented. Their training data was off of one system and then their test data was off of another system. So I think that's one thing to keep in mind. This is also just a ridiculously hard problem if you think about it. Like the sort of problems that I mentioned that were kind of easy are these problems like, you look at the image and you're like, is it dengue or is it malaria or is it, is it a bad mole or a okay mole or something like that? To look at much more like broader health record information with all of its missingness and connect it to the literature, or to even try to analyze the clinical literature and connect it to a medical exam question. These are just way harder type questions. Like if you think about, maybe one thing to keep in mind is that AIs are really good interpolators. And what I mean by that is that if they've seen a couple of examples that are similar, they're able to really well kind of smooth that out. So this type of situation where, you have many patients that are similar to you, and then you kind of smooth that area out and say, now you got a new patient, oh, this is where it kind of maps to. But the sorts of questions like answering these exam questions don't have exactly that property, or the diagnosing from very heterogeneous patient information don't have that property. Not to say that this is not something that we will eventually be able to figure out and solve. I do think that there's headway that is possible to make in this space, but it doesn't have the same pattern as kind of the things that have been easy, which are the things that can be like, oh, I have a bunch of examples. This mole, the reason why this mole is easy, another reason why this mole is easy, I have so many other pictures. I can just map it on and compare to that, that other moles that I've seen in the past.
Excellent, thank you. Our next questions come from Nodari. Nodari, I would invite you to unmute yourself and share your question with our professor.
Hi, thank you for your talk. It's very interesting. So a theme in your presentation has been more of an active process where there's constantly a human in the loop. But what in life critical systems in particular, such as in medicine, or let's say self-driving cars where an accident could cause loss of life, to what degree should an AI perform better than a human, but still make some amount of mistakes before we actually deploy it?
Oh, I see. That is a great question. And I think this actually is like the crux of that last where I ended the presentation, which is like, as a society, what are we okay with? Like, we're okay with a certain amount of traffic accidents, unfortunately, because we view them as inevitable. Like, humans just make mistakes, and we think of them as random. They're not really random, but like, we think of it as just kind of, it happens. And then you could imagine an AI system that actually has many fewer accidents, but it makes them in really specific ways, right? It just doesn't know how to handle a certain type of intersection very well. And then how do we think about that, right? Like, are we okay with that? And I don't think that's a society question. That's not a engineer question to answer. And I think that's what makes some of this really challenging. I will say that there are certain scenarios where you can really just test the heck out of something. I think like second generation TCAS is a good example where two planes coming together, one needs to go up, one needs to go down. And that is a situation where they've tested so many different scenarios, and it's pretty clear, like, follow what the system tells you to do as a pilot. And you can just kind of trust it. But I think what you're pointing to is that there might be situations, or there are going to be situations where you don't have that level, you don't have that, near 100% performance. And then what do you do? Like, are you okay with that, 5% error? And can you identify it? So maybe the productive thing I'd also say is that, to what extent can we recognize when those errors occur and then somehow pass information or pass control back to a human in those cases?
Thank you.
Up next is Nanette Levins. She has a question for you. Nanette, would you please unmute yourself and ask the professor?
Thank you, Professor. I very much enjoyed your talk. It's certainly vital. And I wondered if I could have you take an even bigger picture look and perhaps comment on your experience and any implications for quote unquote informal governance or regulation related to the use of artificial intelligence, whether in the health arena or broader. I wonder if you have any thoughts for us.
Yeah, absolutely. I think we need to be really thinking about governance processes. So in the EU, it's much more organized in terms of GDPR and the AI Act, where they're trying to build some umbrella rules that attach to various different sectors. In the US, it's been a lot more, well, the US law is much more sector specific. So like FDA controls certain things, transportation controls other things. And even within agencies, there's different parts of different agencies are, more or less at different levels of kind of AI understanding. One thing that I think is a reasonable starting point is to say that, especially in situations where an AI is providing an augment or assistance or replacement to a human, that anything that is required in those cases of a human should also be required of an AI. So in terms of monitoring and all of this stuff, or being able to provide explanation of why a decision is made. But more broadly, I agree with you. I think we really do need more regulation, especially around data transparency and around post hoc monitoring. Like in that 2x3 grid, if I had to pick two, I would say really focus on making information about the training data available, so that you know that, hey, this model wasn't trained on people who look like me, or it wasn't trained on places that have my kind of, this car wasn't trained on places that have my type of weather. And also to be noticing when the system goes off the rails. And the reason why I think this is going to need to come from like a regulatory or legislative perspective is that I don't think that kind of companies or in the private sector are necessarily incentivized to make all of this information available. So there are some really big open questions on how to go about doing that. But I think this is a really, really important area.
Our next question is from Peter Barzine. Peter, would you unmute yourself and ask the question?
When an AI model reaches a conclusion that goes against what everyone knows, but with no proof of knowing, how do you proceed?
Yeah, so can you expand a little bit? So is this something where you think that it's wrong? Like you're like, why? Like it says the sky is green, and you're like, WTF? Or is it where it suggests doing something and you're like, oh, I never thought of that. Maybe it could be reasonable.
If everybody knows something, but there's no proof, we could dismiss the AI's conclusion as being wrong, or we might say that the AI has given us a new insight. So how do you decide which to do?
Yeah, and so I think this is a great question, and it has to do with how we and maybe it's, you can think about it as, you know, what if, would it change if it's an AI versus just, you know, your kooky but brilliant you know, friend or something like this that suggested something. So you would start asking for mechanism. You would say, why is this reasonable, right? So that goes to back to the inspectability or explainability, interpretability of models before actually doing it. Or you might tell yourself that, hey, this is a low stakes enough scenario that, sure, we can try going around the block that way and see if it works or not. So I think it's really going to depend on the consequences of the action. And in some cases, maybe you just try it out. In other cases, you seek out some notion of mechanism or understanding. I think it's like there's a, like the AlphaGo case is a great example where like the machine made a very different move, and then, you know, afterwards all these people are trying to analyze, you know, is this changing the game of Go because of this very, very different move that the game has, or the machine has made.
Our next question is from David Rochlin. David, the stage is yours.
Thank you. My question has to do with the possibility of using AI in the allocation of kidneys for transplant purposes, where the supply is so much less than the demand. And of course, there are a whole lot of factors to consider in how those kidneys get allocated.
Yeah, so I don't specifically know a ton about that particular area. I know there's a lot of work in fair and efficient algorithms for kidney transplants, and especially in more of like the theory and the game theory world, where you create these cycles. You know, it might not be in terms of like who's donating to who, these kidney exchanges. So I don't, that's something a little bit outside of my wheelhouse in terms of being more specific about. I don't know what sorts of tools they're using to measure compatibility. I would say there's two parts. There's the measure of compatibility, et cetera, and then there's the choice of prioritization. And the choice of prioritization is a human decision. That's not a machine decision. But the part where an AI could be helpful is you know, trying to make sure that any pairing that's made is likely to succeed.
Okay, thank you very much.
We have a question from our Sergio, and I'm going to ask it for him. What are we in terms of filtering out bias at the input or learning level in the development process of AI platforms? Can we use AI as a filter?
Yeah, I think this is a great question. So, and there's two types of bias maybe that I should point out. So there is the sort of bias that comes from just lack of data. So if your data collection process is not inclusive enough, like no one thought to take pictures of stop signs with stickers on them, and suddenly you have a stop sign with a sticker, and the machine just kind of freaks out, has no idea what to do, output something completely not sensible. And that's really different, I would say, than there's an actual bias in society, for example, with the pronouns in English, or the case that certain racial groups have been targeted, for example, by police, and therefore any system that you train on like past police stops or something like that is going to have a bias. For the latter case, there's a number of really exciting works that are going on to try to make sure that the system doesn't, it's more, I feel like, on the output end or the loss definition end, to say that the input data might have certain biases in it, but the output predictions can't depend on race, for example, or they can't depend on gender or something like that. But I think it is really hard, because if the data are just really, really bad, there's a limit to what you can extract from it in terms of signals. I think we have to also be realistic there in terms of AI is not a panacea. It's not going to be able to undo all of the issues of the, if you put garbage in terms of getting garbage out.
Excellent. Our next question is from Kurt. Kurt, could you unmute and ask Professor your question?
Thank you. My question is more on the big picture view again, because what you've described sounds more in the nature of what some people have called artificial special intelligence.
Mm-hmm.
That is, AIs that are developed for a limited specific context.
Yep.
Today's GPS mapping systems, for example, are another example of that. What's your view of artificial general intelligence, that is, endowing AIs with human-like intelligence, self-awareness, evolution without further human input? So
I'll give you my perspective. I have a very specific opinion on this, emphasizing it's my opinion. So we, as I mentioned at the very beginning of the talk, the specialized intelligence have become commonplace, and I feel like I am way concerned about just, the issues that creep in as, AIs are choosing, recommending our YouTube channels, are, prioritizing our feeds. And I'm just way more concerned about the implications to society from these, special intelligences, are either directly or oftentimes, indirectly, without any sort of maliciousness, acting to prioritize something for a particular company or industry without really thinking about the broader consequences. Whereas with AGI, like we keep saying that, oh, it's going to come in 30 years or 40 years, and we've been saying that forever. I think of AGI as like a near-Earth asteroid. Some people really need to worry about the near-Earth asteroids and know what to do about them. But I just don't see that as a direct concern in kind of any sort of near term, whereas the special intelligence, the myriad special intelligences, I think, are affecting our lives, our elections, our everything right now. So that, again, my personal perspective, I tend to be very kind of pragmatically minded about these sort of things. Few people should be worrying about AGIs, but not a lot. Most people should be worrying about regulating and monitoring specialized intelligences.
Okay, thank you.
All right. We have a question from Thomas Oberst. Thomas, if you would please join us and ask your question.
Yep, Professor, this has to do with COVID. Any recommendations that you would make to our government with regards to some way in which we wouldn't necessarily be receiving mixed messages around around what we can expect in terms of models and in terms of disease progression?
Yeah, well, COVID is new. So I think that is hard. Very smart biostatisticians, public health experts, statisticians have been, making models. People have been crowdsourcing models for how various policies might affect things. And as we see even over the last several weeks, it's such a dynamic situation with new variants coming in and all of this. So I think what we can realistically ask for is maybe reasonable uncertainty bounds, where people don't say, okay, we've solved it, because this is not something that you can say. What we should have learned by now is that we can't say, okay, now we got it, we've solved it. but I don't know if there's a lot better you can do than kind of understand that the situation is going to have these high uncertainties.
All right. And I'm going to let Carlos ask our final question before he then thanks you. So Carlos, you have a question to wrap up the Q&A portion.
Oh, thank you very much. Professor Ryan, thank you very much for the talk. Thank you, everybody, for joining us. We've talked a lot about this with AI accountability. I think in the US, this is not as advanced, but should people have the right to an explanation when they're subjected to these automated decision makings? And what do you think an explanation should look like? I think we talked a lot about this, but I figured if you could share a little bit of your insights to the crowd.
Yeah. So I think people should have the right to recourse if the decision is if something bad happens, or to be able to appeal a decision or something like that, which is not quite the same as having the right to explanation. And then I'll answer in two ways. Like, one is to go back to what are the legal settings in which this lives? So in some cases, your recourse is through explanation. You are entitled to know, for example, why your loan was denied, and an AI should also provide that type of information. In other cases, it's a no-fault policy, right? Like, you get a rat in your cereal, and you don't need an explanation of why you got a rat in your cereal. It just shouldn't have been there, and you deserve some sort of recourse. So maybe, like, if an autonomous car has a crash or something like that, we just say that there is no explanation required. It was clearly the car is at fault, or there's a no fault policy that the person is entitled to some sort of recourse from that vehicle getting damaged or whatever it is. So I will say that I think it's more important to think about the harm and how do we address the harm, and then decide whether the explanation is relevant to addressing that potential harm. And AI systems don't have to do it exactly in the same way as the human systems are currently done, but it should always be that, okay, what is the thing if we do choose to require an explanation, the explanation should provide information to help the person who's receiving the explanation determine whether a particular harm has been done or not, because that's really the goal for why we're doing this whole thing in terms of accountability.
Thank you very much, Professor Doshi-Velez. Thank you very much for everybody for coming into the talk. I'd first like to remind the participants that at 1 p.m. we'll need to join the keynote lecture on advancing educational opportunities to fight inequality by Dean Long. And right now we're going to put in breakout rooms to try to, as President Haggerty mentioned, mimic as closely as possible our dynamic after these talks. And we're very much looking forward to trying to think through these myriads of things. Thank you very much, Professor Finale. I understand you might be able to join us for a bit.
Yeah, thanks everyone for joining. And I can hang out for around 10 minutes or so in the main room if anyone wants to continue to hang out and ask questions or have a discussion.
That was fantastic.
Hello, Professor. I have a question. My name is Erwin Gaines that I didn't get to ask during the session. This is a follow-on to what Peter was asking about when an AI says something that is obviously wrong, and you referenced the AlphaGo. One of the big differences between the AIs that do Go and chess is that they're able to do an enormous number of trials and sort of self-train, because the rules of the game are very, very clear, and the outcome of the game is known. You'll know who wins and who loses. And so they're able to develop strategies that are completely different from what a human would use and seem very wrong, but you can evaluate their correctness by letting them play a game. And if they beat the humans, then clearly they're using a correct strategy. And I'm curious if there's any way to use this sort of thing in health-related applications. Now, again, it's obviously much more difficult because you can't try it out on an infinite number of patients. But if you have good enough models, you may be able to use the AI to find correlations between variables that a human would never, ever be able to figure out.
Yeah, I think this is a real opportunity if we can use AIs to find these correlations. Honestly, like, it's been in our experience that it often ends up being like we discover some sets of correlations, and then the clinicians are like, oh, that makes sense. Like, we didn't necessarily think of that at first, but now we get it. And I think that's kind of that feels comfortable to us, because we're analyzing retrospective data that comes out of these hospital EHRs. And we would be surprised at that granularity of data if we could discover something like truly, novel about medicine, because there's just not even that much variation, in terms of treatments that are being given. But I think it would be interesting. I know that there's work in like more discovery-based settings to try to come up with these like completely novel insights.
So I was concerned with. I mean, one of the reasons why you have 128 parameters is you don't really know a priori which ones are the important ones.
Yeah. So that's what I think. This is where the cleverness comes in. Is that so there were two major things we did, and just for the purposes of keeping the presentation at a high level, I didn't really tease apart those parts. But one big area that my research group works in is saying that if you're interested in managing problem X, can you learn, say, a 5-dimensional model? But that each of those dimensions might be quite complicated. So the way we talk about these are like these are like a concept bottleneck or a bottleneck of some kind. So you still have all the original data. It goes into it gets kind of filtered into a very small dimensional space, and then that very small dimensional space gets used to make the decision. So we're not throwing away the data from the beginning. We're not curating and saying that, hey, these variables are not relevant. What we're saying is our assumption is that at the end of the day, you're going to be able to squeeze all the important information into a couple of key factors, and each of these key factors then can be inspected by the clinician. But they could have really unexpected things. For example, in the case with the hypotension, there were certain of these factors that had to do with like the consciousness of the patient, and they were like, oh, that makes sense. Like the level of sedation affects like how we would choose some treatment recommendations and things like that as well. So we're absolutely not choosing a priori. We're just applying the assumption that the way the 128 dimensional model said is that take all of the patient data and then try to basically reconstruct the patient history. Like take the data and just squeeze it down. Imagine you're trying to do like compression for a photograph or something like that. And maybe you need 128 dimensions to like compress your photograph, to store it in like some memory space. But we don't need to compress everything. We only need to compress the things that are relevant for downstream decision making.
Yep. Thank you.
Yeah.
Any other burning questions that people might have for Professor Doshi-Velez before she has to leave that you weren't maybe able to ask during the actual Q&A? I see Adam Gilfix. Adam, yes, go for it.
Thank you. Sort of in the vein of that last topic, and you mentioned the trade-offs between human interpretability and model performance, and simpler can often be better. But to a degree, do we end up limiting advances in this space by saying, hey, we made this really great model that's super complicated, but we don't really understand what's going on in that black box. And so we're going to err on the side of using something that's a little bit more understood and possibly more
Can you tell me a
interpretable.
little bit more? What do you mean by advances? Like, do you mean like scientific advances or?
So just in terms of, for example, if we take like a linear regression model versus a neural net, right? One is going to be more advanced and more, more
Expressive,
complex.
like able to get better performance numbers.
Right.
Yeah. So I think this is where the cleverness comes in. And I think it's a false choice in many situations. So that this whole process that we went through to try to squeeze something down to these 14 discrete states, we didn't lose anything by doing it. And it actually required advances in machine learning and AI to be able to do that. And I think that's what we're seeing, is that one of the things that has been awesome, but also slightly concerning about like the AI revolution is just like, so how easy, or the deep learning revolution, is it just like how easy it is to apply these models, because you have an architecture, you throw some data, you run it through TensorFlow or PyTorch, and it's just super simple, but then you end up with a black box. And then folks like me and other researchers are saying that, well, maybe it's possible if you're clever about it. If you use a linear regression, you're screwed, like as you say. But maybe there are clever ways to set up models that are still inspectable, because maybe they decompose, like I just said, that it's not you go from the features directly to the output in some linear fashion. Now you go to the features in some slightly nonlinear fashion to the bottleneck, and then from that to another slightly nonlinear fashion to the output. And then by designing those nonlinearities appropriately, you can still model a whole bunch of things. So you haven't lost things in terms of expressivity when it comes to the deep model. But you've kind of carefully designed it in a way that's still going to be, each piece is inspectable. Maybe not the whole thing all at once, but on a couple of slides, you could take a look, which would be a very reasonable expectation or ask from an expert or something like that.
Yeah, that's helpful. Thank you.
I will say just one follow-up is like the one place where I think this is hard is these more imaging and waveform type domains, because there it's like harder to imagine like what's the abstraction. Like, is it that the picture has a beak in it, or the picture has like an eye in it or something like that? But again, many cases it is doable.
Looks like Jay Stone has a question. You're getting short on time, so
Yeah,
Jay Stone,
maybe Jay Stone and Sammy.
and then we'll cut that portion. You can go enjoy the rest of your Saturday.
Hi, I'm Jennifer Stone. I'm on staff at Beth Israel as a hem-onc doc and another hospital, a community hospital. And I was just wondering, I use Micromedics for drug information, but it does have a link to IBM Watson, but I've never been able to use it. When I try to use it for a drug, I'm wondering if you have any experience with IBM Watson in medicine and how we can use it effectively, or.
I see.
Like
Sorry, that one's out of my wheelhouse. I don't have experience with Watson.
Okay.
Yeah.
All
If
right.
you find out, I'll be very curious.
Yeah. Well, thanks for your help.
Yeah.
Sammy, you had a question.
Yep. So my question is really, do we need to make causality a core component of our model building paradigm? And as we're doing that, should we be more explicitly addressing the effect that confounders can have in our attempts to draw relationships between inputs and outputs?
Yeah. So I think if we can get causality, we should be using it. Yeah, for sure. I think the trouble is that to get things that are causal in many situations is just really, really hard. We just know we're missing loads of confounders. Like if we collect, even like the ICU is maybe a relatively easy setting because so much is being measured about the patient. Yet any intensivist will tell you that, that's such a small fraction of what they're using when they make decisions, or is it, or not small fraction, it is a fraction, right? There's really lots of other important things that they're looking at, and other areas of medicine even more so. So this is where we've kind of moved toward interpretability or inspectability, to be able to at least identify when there's a confounder missing. For example, when we were doing this work in the ICU, we realized that as we were making the simpler model, there were certain variables related to fluid balance, like how much fluids have you already given someone in the past, and how much has come out, that were just not being captured in the initial data set, and they were crucial. And so, the doctors looked at it and they were like, the thing that's probably distinguishing this fork in the road, it's not a real fork in the road. It's because some of these patients probably had this type of fluid balance and some of them had this other kind. And that's really why it looks like disagreement, but it's not really disagreement. It's a confounder we didn't measure. So I think our best hope is to be able to use causality when we can. And then when we cannot use causality, we provide inspectability to be able to have hopefully the expert determine whether it's causal or not.
Super, thank you.
Awesome. Well, thanks everyone for hanging out a bit more. I'll also just say, I'm really interested in questions around AI use, AI ethics, AI policy. So if any of you are kind of in this space and would ever like to chat with an expert who works on the actual maths but is really interested in the legal and regulatory frameworks and policy frameworks, I'm definitely happy to be here as a resource.
Would you like I can share your email address in the chat if it works?
Yes.
All right. Well, thank you so much, not only for this amazing presentation, but also for staying on and answering a few more questions.
Yeah, my pleasure.
So thank you again. I'll be in touch soon, but I hope you enjoy the rest of your Saturday.
All right. Likewise, everyone enjoy the rest of your day. Take care. Bye.
And everyone else, you are welcome to stay on and continue the conversation. You don't have to go into a breakout room. You can chat here in the main room if you so choose.